my privilege today to introduce Matt Rossi. He is currently a research scientist at Earth Lab, and he earned his PhD in geological sciences from Arizona State University and a BS in geology from the College of William and Mary. Prior to that, he was a visiting assistant professor for the program in environmental sciences at Northwestern University. And he classifies himself as a geomorphologist. And his research focuses on the relative roles of climate, tectonics, material properties, vegetation, and hydrology on setting the form and function of rivers and hill slopes. So with that, we are very excited today to hear his talk about the accuracy assessment of binary classifiers across gradients and feature abundance. So thank you, Matt.
Thanks, Alton.
Okay, so we can just move her off.
Like, this is like testing me truly because I always use a mouse. There we go.
Okay.
Perfect. All right. Well, thank you. Thank you for inviting me to talk today. And yeah, I'm gonna speak a little bit about some relatively recent work, though I'm gonna kind of motivate it with some work I've done in the Colorado Front Range as well. And I'll just start, see if it advances. Let's see, not quite yet. Right now. Okay, so I'll just start with a simple problem statement, which is we need binary classifiers for a lot of different applications. I'm a geomorphologist, so I'm particularly interested in the surface of the Earth. And if we're talking about features, we can talk about all kinds of features, but when I talk about features, I'm actually talking about physical features. And those are the things that we see at the surface of the Earth. And so a lot of the tasks I am posed, that are posed to me are saying, well, what's the frequency of this particular morphology? Or where does this morphology occur and where doesn't it occur? And I am going to make another claim here, which is that we need classification techniques that work across gradients and features abundance, which is a little bit of a challenge when we use some of the conventional metrics for quantifying accuracy. And again, for my particular purpose, it's because I want to test process laws, geomorphic process laws that make predictions about the relative abundance of different features. So what do I mean by all this? So I might start with something that I'm looking at. I'm going to talk a lot about bedrock today, bedrock outcrops today. And I'm going to come up with a method to say, okay, I found where bedrock's exposed on the surface. And I'm going to actually go to a real landscape where it's going to be very heterogeneous, right? So this is actually, it's not in Boulder Creek watershed, but it's a little bit south in the Rampart Range. And there are these large 50-meter tall tors all over the landscape and surrounded by a soil mantle. So it's very heterogeneous, and I want to know where there's rock and where there's soil. And there's also a lot of trees, so that makes it a little bit harder just to use air quotes to do it. And then the kinds of process laws I might be interested in, this is just one example related to rock, is this classic idea that soil production rates are related to how thick the soil is. So we expect fastest soil production rates for thin soils and slow soil production rates for thick soil. So maybe where we observe rock are places where we can test such ideas, because if we don't have any soil, then it's telling us that either the soil production rates are slow or the erosion rates are fast. So again, these are ways that we can use observations of the surface to kind of test some of our ideas about surface processes. So this example I'm going to motivate with is just an outline of the Boulder Creek watershed all the way out to its outlet at the range front. I've got it color coded a little bit. It's a 1 meter LiDAR hillshade that is colored with yellow and red. You can think of those yellows and reds as places where I think I've identified rock, okay? And it's actually built on this earlier work where we were looking at material properties and potential flash flooding associated with the material properties. And again, we found that perhaps where rock is situated in the landscape might be really important to runoff generation process in this particular landscape. But I just want to point out 3 things in here and why it's important to be able to measure these things across gradients and feature abundance. One thing to think about is that just looking at this hillshade, we know that there are different physiographic domains when we're going up into the Colorado Front Range. And many of you are probably familiar with that as you've driven up Boulder Creek, right? When we get up to the uplands, we are impressed by the dramatic rock that's exposed in the glaciated headwaters of Boulder Creek. But I'll point you to the fact that if we go a little bit lower down, say where Netherland is, right? All of a sudden we're on this rolling, still relatively steep, but I would say modest for a mountain landscape. It's much more soil mantled, much lower abundance of rock. And we actually think of this place, the term we sometimes use to call this place, these kinds of places is this high elevation, low relief relic surfaces, because we think that some erosional signal hasn't actually punched through and started eating away at that part of the landscape. But before you got there, you had to drive up these steep incised river canyons, again, where a lot of rock is exposed, in this case, for a different reason. In this case, it's because the river's incised down, it started stripping the soils, and we've started to expose a lot more rock. So these numbers that I have all over this map are basically places where I spent a lot of my first years here at Earth Lab painstakingly mapping out rock from air photos. And to see what it's almost sad sometimes looking at, you only get 100 by 100 meter box, and it takes you a couple of weeks to do it. But you can see the kinds of data, truth data, that I was trying to generate in these landscapes. And basically, in this particular, I should say this now, the advantage of doing this air photo mapping is that I can go to places where I can observe rock. So say there's been a fire, or because it is not covered in the forest canopy. So I have high observation of the rock. The beautiful thing about LiDAR data is that it can actually see through the canopy. So if I can calibrate some classifier in the places where I can see, then potentially I can stick that on the entire landscape and start quantifying how rock abundance is varying in the landscape. And so, I wasn't super familiar with a lot of the methods in the data sciences when I came here. And so I followed, of course, what I had done before and what previous authors had done in other landscapes, been very successful, which is simply to say, okay, here's the strategy. Go out, look for places where you have a little rock and a lot of rock, map it, and then build a classifier and see how well the two are related. And if they're correlated, then great. And in particular, I've been using a lot of metrics I've been using for this particular problem are slope-based metrics, because there's this great physical reason to think that slope should be correlated with where rock is. So sediment materials tend to not get any steeper than the angle of repose, which is around 30, 35 degrees. And so therefore, when we see very steep parts of the landscape, that's a pretty good indication that either something's happened that stabilizes the soil, or that we have very cohesive bedrock exposed in that part of the landscape. So slope's actually been a very useful tool for me. But one thing I want to emphasize about this is, in fact, slope works pretty decently, at least at the patch scale in this particular landscape. But it isn't, this kind of treatment is entirely ignoring pixel level accuracy. It's not telling me whether or not the place where I mapped rock in my classifier is the same place where I saw it in my air photos. It's just telling me that at the scene level, I have the aggregate statistics correct. So I want to push further on this. So here's an example of one of those patches. This is patch 1, I believe. So it's right at the mouth of Boulder Creek as it empties into the plains. And it's very rocky. I would say, I think this is order 60% rock in this part of the landscape. You can see an example here of the air photos. The air photos I was using for this was from Pictometry, which is a private company. They're 2.5-inch air photos. The nice thing about this was that they covered a lot of area in the landscape. So it would have been hard for me to say drone all this part of the landscape. And so I was able to do it in lots of different parts of the landscape. But hopefully one of the things that this one example shows is that right off the bat, the truth data that I'm using has uncertainty associated with it. Because I am going through, I can go out in the field and I can verify some things, but honestly, it's very ambiguous as to when you are seeing bedrock versus loosely consolidated rock versus what we might call soil. And so there's actually, right off the bat, some uncertainty in generating the truth data that I'm going to use to calibrate my LiDAR proxies. And also, of course, I went and picked places where they're pretty high visibility, but it's not perfect. There's still trees in even the rockiest places. Fires the vegetation grows back, so I have to work fast, right? So there's still going to be uncertainty in that. And so, there's this trade-off between wanting to look at as many places as possible where I can map but also trying to maximize how much I can see of the surface so I can get really high quality maps. But of course, then the other side of the uncertainty is in the classifier itself. And this too has many different potential sources. One simple source of potential error is just if I have two data products that were generated off of different remote sensing platforms or field platforms, then the co-registration may not be perfect, right? So there might be some systematic offset between my two data sets, right? I'm calling that co-registration error. There might be some problem. You can notice I tried to overmap the rock as much as I could. So I went beyond the scale of the 1 meter LiDAR so that I could re-aggregate it back to the LiDAR scale. But we don't necessarily know what that scaling is as we look at really small bits of rock and how that scales up to, say, a coarser LiDAR 1 meter DEM. And then, of course, the model error itself, right? So I use slope as the primary input to this model, so that's going to be an imperfect proxy. I can imagine many scenarios where I have low slope bedrock. I mean, think of a bedrock river channel. That's going to have very low slope bedrock exposed. So there's lots of reasons for us to expect other sources of error. So to this end, I kind of revisited some of these ideas, but in kind of a synthetic world where I could try to understand how some of the more common metrics for evaluating pixel level accuracy perform if you try to use them across gradients and feature abundance. I'll just make this statement right now because it kind of anticipates something you'll see over and over again, which is that a good pixel level classifier accuracy metric should account for all four classification outcomes, the true positives, true negatives, false positives, and false negatives. This is not universally true. In fact, one of the ones I'm going to show doesn't. In this particular case, one of the more common metrics is F1 score, which basically it's telling you how well you did at classifying the thing you're looking for, which means that it's asymmetrical in that the thing that in this case I was looking for was rock, so it ignores the soil. So in this particular calculation of F1 score, which kind of balances my type 1 and type 2 error equally, so it doesn't penalize one kind of error over the other, it doesn't actually account for true identification of soil, right? And so there's no intrinsic reason why I should want to classify, in this particular case, want a classifier that only did well on rock. There are other applications where that might be desirable, but not this particular application. So I adopted another pretty commonly used metric as well, referred to as Matthews correlation coefficient. No relation, not me. Not naming things after myself here. But basically what Matthews correlation coefficient, you can imagine it as I've put this little bivariate plot here of the actual data versus the predicted data. And you've got zeros and ones. This is a binary task. And so I've sized my circles to the number of observations in that scene to the left. So you can see there's a lot of true negatives. That's anchoring the bottom left-hand corner. It can also be summarized in something many of you are used to seeing, like a confusion matrix here in the colored corner. But the point is that all this correlation coefficient is a regression of that four-cornered plot. And it's telling me how good am I at accounting for all four components of the confusion matrix. So this actually wasn't a particularly good, it didn't do a particularly good job, at least at the pixel scale. It's a decent job. I think there was likely a lot of issues with co-registration errors between the two data sets, which is leading to this error. So this is when I asked myself the question, how do these accuracy metrics perform when the whole goal for me to build a classifier is to use it where I have 10% rock and where I have 80% rock? And this is potentially a weakness of some of these pixel level scores. And so I just want to see how they behaved for a whole bunch of synthetic examples. And this is work that I've submitted and it's not yet published. So you should give me all of your feedback so that it can get better because I'm doing the revisions on it now. But the general approach is simple. It's to generate synthetically true feature locations, to generate my model feature locations, and then calculate accuracy scores between the two. And I'm going to have certain kinds of relationships between the truth and the model data so I can understand how that plays out if I was looking at a gradient, say, bedrock exposure. My baseline case here is, here's an example of one of these synthetic landscapes I generate is having all of my features to be 1 pixel in size. I'm going to enforce the idea, for the most part in all the examples I show, that the scene level properties match between the model and the truth data. So if I had 50% rock in the model, then I'll get 50% rock in the truth. This is kind of a worst case scenario where that I'm showing right now. This is a 50% rock scenario, and I've got it colored by the 4 components of the confusion matrix. But it's a worst case scenario because I'm saying that the scene level fraction is the same between the 2 scenes, but the locations are independent of each other. So a good accuracy metric should diagnose this case, right? Because it's saying locational positional accuracy is independent in both the model and truth data. Good news. So when I use Matthew's correlation coefficient, that's this red line here for this scene that I'm showing right now. And excuse me, this is actually a normalized version, so they scale in the same space, so they scale from 0 to 1. But the thing that you see is that regardless of whether I'm looking at 5% rock or 95% rock, the Matthew's correlation coefficient is diagnosing that the 2 model truth data sets are independent of each other with respect to location. Now, F1 score doesn't do well, and you'll see this over and over again. It actually is known not to do well for these kinds of problems because one of the kind of basic premises of using F1 score is that you have similarly balanced data. So you're not looking across big gradients in feature density. But just to emphasize this point here is that if I were to use F1 score across a gradient bedrock fraction, I would see this kind of spurious positive relationship because it accounts for both the accuracy of the metric as well as the actual proportion of rock in the landscape. And that's because it's not accounting for those true negatives. And interestingly, if I just guessed for all these scenarios that all the landscape was rock, I would do better than if I enforced the condition that they match the scene level property. So actually adding information, in this particular case, the scene level information is worsening my score. Tested this for a few different things, because I'll show you a few more examples in a second where I'm going to start playing with the size of features and the shapes of features. Same exact setup. This time I make my bedrock features 10 pixels by 10 pixels instead of 1 pixel size. Now, of course, now there's 2 correlations going on, right? So you have what's the distribution of features in the landscape, and then how big am I? So I'm correlated with my neighbors, right? So there's 2 scales of which the correlation is going on here. Now, I will say this, is that it really doesn't matter how big I make these things, but I do need larger domains to actually get enough population statistics to recognize that they're independent of each other. So if I had one big tor in the middle of my patch that I was mapping, or one big bedrock exposure, and it could by chance very easily have a model that also modeled that same big tor on top of it. So I need to look at larger areas to diagnose whether or not those 2 data sets were independent of each other. Okay, so now I'm going to march through. This is the basic setup for everything that I've done. I generate these synthetic features. I look at the model in truth, I calculate the scores, look at the patterns as a function of bedrock fraction or feature abundance. First, to me, the simplest next step is to say, well, what happens if I impose a constant random error into the landscape? So we can imagine this being the case of I have a 5% error on my ability of my classifier to identify rock, right? But otherwise, it should be high fidelity. So there's some fidelity with the model and the truth, but there's some error rate until you go to 50% error, which looks like it's random again. So the thing I'll just point out here, so this is kind of like that initial example I showed from the Boulder Creek watershed. You put the true fraction on the X and the model fraction on the Y, and you start going up from 5% error rates in the solid line, and then you go to the bold dash line to 50% error rates, is that you do get a strong relationship if you just add a constant error to the data, because I'm applying it uniformly across the landscape. But when you're near the end member cases, you do preferentially modify the more abundant class. So that's why they have intercepts. That's why none of these lines will go to 0 unless I had 0% error, right? So if I had all soil and I had a 5% error rate, then 5% of my soil is going to just by chance be turned into rock. And that's going to give me that intercept. So what this looks like in the accuracy scores, so now we can take the same kinds of plots, same kinds of contours, bedrock fraction on the x-axis, now I'm showing the accuracy scores on the y-axis. You can see that the Matthews correlation coefficient is actually doing a pretty good job in that it is symmetrical, so it's not like doing anything weird in terms of asymmetry, but it's also for a large domain, say 20% to 80% rock, it's giving you the same results regardless of where you're measuring it. Now, near the ends is doing very poorly, and that is directly reflecting what I said a second ago, which is that you preferentially modify the more dominant class when you get to really small abundances or very large abundances. Okay, good. So then the next natural thought in my head is to say, well, what happens in my clearly challenging case that I showed before if I just take all of my truth data and my model data and offset them by one cell, one pixel, which to me simulates the case of co-registration error, right? We might imagine there's 1 to 2 to 10, however many pixels, depending actually on the scale of the data I'm using. What does it do to these accuracy metrics? So in this case now, the error rate, and by error rate here, I mean the total error rate. So that's including anytime you get the answer wrong, okay? It is low at the boundaries because there's not very much of the feature. So for instance, if I had all soil and very little rock, and I put a 5% error rate on the or a 50% error rate on the rock, well, there's only a few pixels, which is so the overall error is going to not be very high because, in fact, I have a lot of true negatives, right? And on the other end, I have a lot of true positives. So we have this behavior where, in fact, you get a relationship between the error rate that is asymmetrical as a function of bedrock fraction. And the asymmetry arises not for the initial case where we just had one cell features, but the cases where we made our features have some size associated with them. So that's what I'm showing here in the dashed lines as they go down to the black, which is a 10-meter torus. So I'm going from 1 to 10-meter torus. And again, when we look at it in terms of their accuracy scores, again, we always are going to get the spurious relationship that's modified in some weird way with F1 score. I keep on showing it, though I probably should have stopped showing it a while ago. But interestingly, for our Matthews correlation coefficient, we do get decent behavior in some domains, but we get some sensitivity at the high end of bedrock exposure. So I got curious about this. So I want to step back for a second and think about how I'm actually simulating my features in this landscape. Again, with an eye towards features I might map in the real world. Now, in all the examples I've shown you, my bedrock features are little square pods. If they overlap, they can make more complicated things, but I'm randomly placing squares all over of some size all over the landscape. We could imagine starting with different seeds. We could imagine starting with circular seeds or pluses or stars or all kinds of things, right? Now, it gets hard to get complicated seeds as you get smaller and smaller. So I went to the scale here, the right-hand column, they're approximately the same area. So that square is approximately the same area as that star. They're off by 1 pixel. And we can see what happens when we just impose a simple linear offset, is that the frequency, and again, I'm color coding the false positives and the false negatives here, by just shifting it in one direction. And these are all rotation symmetric, so it actually doesn't matter which direction I shift it. I'm shifting them all to the right here in these figures. But the square produces the least amount of error. And this star, oh my, the star is quite problematic because it actually produces more error than the size of the shape that I made, right? And so we can see right off the bat, just from this like simple thought experiment, that the shape of these objects and how it interacts with that systematic error should matter. So here's an example of like a little landscape I might have created in my numerical setup. And it's just showing you my random placement of features with dots. And then I've aggregated them into actual features, right? So if they overlap, you get to be one feature as opposed to two features. I didn't emphasize this in the previous slide, but one thing you'll notice right away is I make my features larger. my features become less sensitive to this offset error. And that should make some intuitive sense, because if I have a 1 pixel shift and I'm only 1 pixel, then I'm always just moving to the wrong place, right? But if I'm a big feature and I have that shift, it's relatively smaller magnitude effect on my classification. But complex features, and by complex, I mean that have complex boundaries, are more sensitive to this offset error. So that star was a very complex feature compared to my square, which is a very simple one. And that star could produce a lot of error because everything was disconnected. So here's a good use of F1 score. And because in this case, I just want to think about shapes right now. I don't want to think about where the shapes live. I'm just thinking about shapes within a matrix. And so I'm just plotting up here the F1 score for different average feature areas. I showed all the points almost all the points came from the previous slide, from all those shapes I showed you, right? I tried to get their symbols the same too. So I've got stars and rounded ones and pluses and squares, and that dashed line is showing you it's very easy to calculate what you expect the frequency of false positives and false negatives will be for the square. So I just plotted that up so you can see it as a bounding envelope. And then I'm showing this example from potentially one of my synthetic landscapes, right? And I guess the thing I want to point out here is that it is not a requirement that average feature area will lead to better scores. It is itself a function of the shape of that area. So we need to understand something about the shape of the features that we're trying to find. And so I'm going to go back to this somewhat interesting result that for me, from my naive worldview, was quite intriguing, which is why did I get this asymmetry in this accuracy metric that is designed to be symmetric? And I think the reason is actually pretty straightforward, and it's because the way that I set up my synthetic scenarios was I said, I'm going to change two things. I'm going to change how abundant the feature is, and I'm going to change the initial size of the feature, right? Those are basically the two things I varied. Well, this plot here it's kind of like the shapes I was showing before, only this time I start with a 1 pixel feature and I let it grow to some area. And these are all made up. I just made these up for illustrative purposes. And then I look at the equivalent one if I just had a square, right? And so you can see right away, if I looked, and it might be a little bit small to see, but there's these F1 scores that are listed on top of each of those features. You can see that making a large feature with a square is going to be way less sensitive to that systematic error than making a large feature with coalescing small squares, because it's making more complex shapes. And in fact, I can do this for that run that I showed you with the systematic error. Basically, this plot is showing now the average feature error of my synthetic examples with F1 score on the y-axis, the gradient going from my 10-meter tours, which are doing better than my 1-meter tours that are down at the bottom. And then I've marked the points of where we sit in that abundance space. So you can see the first point is 20% rock, the second point is 40% rock, the third point is 60% rock, and it's marked on all the lines. And so I guess, and then I've got that black line is the scaling relationship you would expect just for a square, right? Just like I showed before. And I guess the point I want to make is that is the interesting dynamics that's going on when I was setting up these synthetic scenarios, was that I was increasing the area of my features at the same time that I was increasing the complexity of those features. And in fact, the score that I was getting was reflecting the trade-off between the competing effects of complexity and scale. So, a little short. I have some more things I can show you, but I'll just leave it here with a few kind of takeaways as well as a couple kind of thoughts to pursue after this, which is, I think we can safely say, and this has been said by many others before, that we should be using these, at least this is one of a number of metrics we could be using, Mapping's correlation coefficient, that accounts for all 4 components of the confusion matrix. If we're going to be calibrating our tools across gradients and feature abundances, this is an absolute must, right? Because these other scores are just going to do very poorly if we have imbalanced data. But interestingly, I think care is still needed in using some of these more robust metrics, because especially near the end member cases. So if you remember that initial case, just random error, because I am going to preferentially modify my more abundant class in that case just by having random error. So I can't compare those sites with more abundant features. And so, and the same thing is with the issues with the systematic error, is there is structure in how we expect these accuracy scores to vary as a function of abundance. That is not what we're looking for, right? At least when we set out to, pick 10 plots, train a model on it, and then go use it, right? We want them all to be giving us the same score and be treating it the same way if they have the same error structure. I think I've convinced you or shown you why these accuracy scores will all be sensitive to systematic error if the error is non-random to the scale and shape of those features. So that's something we have to think about, because oftentimes that's the thing we want to measure, right? We want to look at the shape and scale features, but if we're then training our models to actually the building in a sensitivity to the shape of those features, we don't know exactly what we're seeing. And then finally, I guess this is the more thought question, which is now I was imagining the cases that I was trying to do, which are the cases of using 1 meter LiDAR and something higher resolution to calibrate my topographic proxies on that 1 meter LiDAR data. But as we move to higher and higher resolution data sets, we're inevitably increasing our resolving power of the sinuosity of features, right? And so it may be that even just doing the same analysis on the same truth data, but at different scales of the classified data, will lead to potential systematic biases that are embedding things about the scaling behavior of the features we're trying to map out. And I will stop there and ask for questions. I have more things to share.
Yeah, you kind of addressed my question in your last bullet point there. I was like, well, you can increase your scale also by decreasing the resolution rate. But I guess I'm curious if you did any experiments where you were changing the relative resolution of your model and the data, the LiDAR data.
So I tried to be careful when I started talking about my synthetic landscapes, is that I only said pixels. So I actually didn't, so in a sense, they're scale independent. So the question you're asking would be like, well, if I add an actual data set, where would it map into my synthetic world, right? Would I have big features with respect to the resolution, or would I have small features with respect to the resolution? And then you could do that translation between the two. So in my case, I have coarse features with respect to, I actually don't know the scaling properties of all the rock that I'm mapping. So I have, it seems like the more that I map, the smaller things I can identify. And so I think I'm spreading it out across a lot of different scales, but I don't think there's a direct analog to the synthetic ones I have where I've kind of bludgeoned with one scale. I forced one scale on it.
Yeah, well, I guess what I'm saying is that when you're calculating your accuracy metrics right now, it seems like your model and your data are the same resolution. And like conceivably, you could run a model at much higher resolution or much lower resolution than data, and then that would affect your accuracy scores.
Yeah, no, so for sure. So in practice, what I do is I resample the higher resolution data to the coarser resolution data. So I am doing those things at the same scale, but I don't know what's happening in that rescaling. So, but that's a huge question for sure, knowing what to do with that.
That one. So are you sure you're not a geographer? I guess I have my questions about the backstory. Like, how did you go from kind of identifying your own training data in a 100 by 100 meter square to this pathway? Like, what led you here?
Well, so, one of the, I would say, insidious things about doing detailed mapping is that you do it and you say, oh, wait, but I could do it. You figure out ways to do it better. Mm. And so I started flying drones in a different part of the Front Range. And I was like, oh, this is working so much better because I am seeing more. But my ambiguity, if I go all the way back to the beginning of like my ambiguity about what's rock and what's not rock and mapping truth, it still retains, it's just now at a finer scale. There's still ambiguity and same amount of ambiguity. I'm just looking at cooler looking things. And so that's what really got me interested in this question, is because I was like, well, wait a second, I want to do better. Like I knew I was kind of tangentially aware of how I could incorporate some of the kind of machine learning approaches towards classification. But then I was like, well, wait, they all say don't do this on imbalanced data. And almost every application I have is on imbalanced data because I want to be able to test those process laws. And so that's kind of what led me down that route.
And then how good does the data have to be in order to answer geomorphology questions? Like, do you know what I'm asking?
Yeah, so this is, I mean, so yeah, there's maybe an implicit question here, which is, do I need the pixel level accuracy for the applications that I was showing or not? I actually think that bedrock map that did so poorly, actually I think is working quite robustly across the landscape. Like the classifier built from that, I think is actually, I can't say quantitatively, but I can say semi-quantitatively that it's working well because, you know, there's kind of the scale of like, I was mapping the aggregate statistics of these patches, and the patches were like my points as opposed to the individual pixels, right? And so, you know, I don't think the answer to that question is easy, mostly because it depends on the scale of the problem you're trying to tackle. So there's like, from my perspective, there's three scales. There's the scale of the data you have. There's the scale of the kind of sampling strategy that I used here. And there's a scale of the problem I'm looking at. And those scales are all interacting with each other and pulling on each other. And so I think for every problem, it's going to be a bit different.
Yeah, I was just curious about your training data and how you like selected the area, like where those plots were and like.
From the actual places?
Yeah.
Well, the first criteria was that pictometry footprint. So I knew that that was going to sample into my high elevation, low relief surface. I knew it was going to sample down into the steep, rockier incised rivers. So that was my first criteria, is like, where can I move around? And then I basically tried to spread out my non-quantitative assessment of rockiness across the full range of bedrock exposure. So I basically was trying to pick a couple near zero, a couple kind of at low medium, a couple at, and mapping the actual visibility on top of that meant that I was actually left with a lot fewer places to work on. Because like, for instance, it's really hard. Like there could be biases in my truth data because, you know, north facing slopes tend to be more productive slopes that are covered in tree canopy. And therefore, if there's something important about aspect and rock exposure, which is actually where this work is heading in my actual kind of science questions, I actually have a bias in my calibration data because the places I can see the rock are the south facing slopes, not the north facing slopes, because they're covered in vegetation canopy. And I actually think there's a strong aspect dependence on rock exposure. So yeah, so it's a great problem, but I was very opportunistic.
Thanks.
Kind of going with that, like your like plots, I guess, for your truth data were 100 square meters. Is that what you said?
I think I showed examples of 100 by 100. Because of, you know, I showed you the sensitivity when I used coarser features. I actually did the analysis on 1,000 by 1,000.
Okay, yeah.
So I scaled up by 10 just so that I could get, as soon as I got worried about like, what was the pseudo random seed I used, I was like, okay, just make it bigger so I can do the statistics better.
And so this may not actually have mattered at all, but I'm thinking about the influence of like spatial correlation, spatial autocorrelation between like your train and test sets. And when you have these like square plots across the landscape, when you scale that up to the landscape level, how does that affect your ability to assess these accuracy metrics?
Yeah, I think that would be absolutely the next thing to do, would be to actually, because right, the confusion matrix collapses a spatial error structure into non-spatial error structure, right? So like even the things that look the same in Matthews correlation coefficient are actually quite different in terms of their spatial autocorrelation structure. And so I actually think that is the thing to do, is to like start building different autocorrelation structures and then doing the same thing I just did. I was kind of building up from my simplest naive understanding up, and that would be the next thing to do, is to like tinker with different autocorrelation structures. Yeah, for sure. And also, so one of the things that it also started, so the other example of like, so another project I work on bedrock exposure and steep landscapes. I'm also working on these funny things, which are these MEMA type mounds. This is a Fluorescent Fossil Beds National Monument, and they're kind of these enigmatic little features. They're like little dimples on the landscape. People like to say vegetation and hydrology are causing these feedbacks where you get like uphill motion of sediment transport, right? People like gophers. Gophers are a popular mechanism to exploit. People like paraglacial processes. But these things, this is a national park. They hadn't been noticed until like 5 or 6 years ago. The park scientists contacted Bob Anderson here at CU and said, what are these things? These are cool everywhere else. We have them too at our national park. And so, it's the same kind of problem of like, we're just at the limit where the 1 meter LiDAR can actually resolve these features. But notice that a very fundamentally different characteristic of these kinds of features is that they seem to be space filling. They're not random, like they're organized in a way where there's a characteristic scale between individual mounds, which probably reflects something about the dynamics of the process that's forming the mounds. And so then, as soon as I did my little synthetic examples, I was like, oh, well, I need something that actually enforces this characteristic scale on my features, because then that's going to produce a very different set of patterns than the way I was randomly letting things coalesce in the landscape. I actually think another cool application in the same vein would be to take some of our models, our kind of process-based models, and generate features with a very set of abundances of whatever feature we're looking at, and then sticking these same metrics again on those. So I think there's lots of ways to poke at this from different directions, as opposed to just coming straight from like the data side of like, here's what I see, what do I do? But yeah, I think there's kind of all kinds, because right, if I densify, I don't know if you guys have seen the MEMA mounds in like the Merced area of California, but they're huge and they're dense, and like, so you can only enforce that spacing for so long, right? Here they're kind of subtle and kind of low amplitude, but yeah.
Super thought-provoking for all kinds of reasons. I'm most intrigued by this, like, as spatial complexity goes up, so does air. That makes total sense. I mean, if you have a fractal structure, it doesn't take very much translation to get like infinite air. But it seems like in your system, there's a bit of a directionality. It's like you have it as slope as like a direct variable, but it's almost a bias also. And I've seen people in like range limit maps translate them rotationally and then map the air as you translate. Mm-hmm. So if you have like a river basin that's totally asymmetrically fractal, as you rotate that through, you get a really like characteristic air structure developing. So you might be able to do some rotational stuff.
That's good. That's an interesting idea.
See how that maps and see if you can say, oh, like there is in this landscape, there's a directionality. So I don't have to add slope. I can use that directionality as a feature.
It's an interesting idea. Yeah, no, I mean, in my like little play world, it was all about enforcing rotational symmetry so that I could do simple things and understand what was happening. But in a sense, what you're proposing is leverage the observation of that asymmetry in the real world to see if you can understand something about its sensitivity to air structure, which is like flipping on its head, which I think is a cool idea.
And presuming that across the landscape, they all have the same general symmetry bias. And so as soon as you identify it one place, you can sort of project it everywhere.
Thanks, that's a cool idea.
Super thought-provoking.
Are there any questions from folks online? Feel free to unmute yourself and ask a question if you have any online folks.
Another question. I realize that the whole thing is about binary classifiers.
Sure, yeah.
But it seems like potentially part of the solution could be a classifier that gives you a probability of it being in a certain place, right, with the co-registration error, you would likely end up with, not 1, but 0.7 or something on some of those areas. Have you looked into at all?
So you're talking about like fractional spatial error. Right, like if there's, that's a good idea. I mean, there's no reason why I couldn't just do that, right? I mean, that would be pretty straightforward to implement. I just have to have a scheme for how I was doing my resampling of that offset.
Yeah, I guess some kind of model of your model.
Yeah, exactly. I imagine I could put a few different things in there too, and they would do different things. But yeah.
One clarifying question, which I didn't quite understand how you were using the word gradient. Did you mean the?
Yeah, hard. Yeah, especially when I talk about slope all the time. And I'm literally talking about slope. I'm talking about rocks falling down hills. So yeah, no, in that sense, I was using gradient in its more generic sense.
Yeah.
And it with the idea that being, the gradients I'm imagining for the example I showed are erosional gradients or soil production gradients, which could be embedding climate gradients, right? Like there's all these potential gradients I could be thinking about that would connect to some, law that we think we know about surface processes and predict something about the probability distribution of those features. So like there's this really cool paper. It's now been like, 10 years, but it's called the topographic signature of life. And one of the arguments they made is like, wherever you look, you can find things on Mars that look kind of like things on Earth, right? It's not like there's some uniqueness to Earth, but yet Earth is super unique, right? And so one of the arguments that they made was that maybe the place we need to be looking is in the probability distributions of those features and not just like some diagnostic form. Because in fact, there are only a handful of forms we have available to us in both the abiotic and biotic world. And that in fact, kind of these kinds of approaches that are looking at the probabilistic structure of those occurrences might be more telling. So that's kind of always been sitting in the back of my head too about how can we better build probability distributions of things we think we observe. And now that we can see them because we have high resolution data.
Okay, thank you. I was thinking on a different.
Cool.
All right, thanks,
Feel free
Matt.
to ping me on it anytime.